Hey everyone, this is 13.1 Basic Probability Theory. On this first slide here we have a couple definitions that I want to talk about and go through. So the first thing is an experiment. This is any observation of a random event. For example, this could just be rolling a dice and seeing what number comes up. The outcomes are the different possible results of the experiment. So if you roll a dice, there are 6 different numbers that could show up. And the sample space is the set of all possible outcomes. So again, if you roll a dice, your sample space is the set of 1, 2, 3, 4, 5, and 6. A very common example is if you roll 2 dice and you want to see how can you get a sum of 5. We talked about this a little bit in the counting section, chapter 12. So you might recognize this table here. This is all the different outcomes if you roll 2 dice. So like this first one is you could roll a 1 and a 1, a 1 and a 2, a 1 and 3, etc. Or a 2 and a 1, 2 and a 2, 2 and a 3, etc. All the way down to 6 and a 6. There are 36 outcomes here because there's 6 options for each dice. And if we're looking for all the ways you can roll, so the experiment here is just rolling 2 dice and seeing what the sum is. This is the sample space. And if we're looking just at getting a sum of 5, those are the values here, 1, 4, 2, 3, 3, 2, and 4, 1. And we actually say that those would be the events. So the event rolling a total of 5 would be the set of 1, 4, 2, 3, 3, 2, and 4, 1. And we say an event is a subset of the sample space. So it's just one or more outcomes. So again, the event of rolling a total of 5 is the set of these 4 outcomes. And we're always looking for the probability of events. So events are kind of what we're focused on. Alright, so a little bit of notation and some definitions here. P of E, this notation, sometimes we'll read P of E, but it really stands for probability of the event E occurring. And probabilities happen to be numbers that are between 0 and 1. Right? They're never negative, and they're never more than 1. If you have a probability of 0, that means that event is impossible. It cannot occur. It would be like saying, what's the probability of rolling a 7 when you roll 1 dice? Well, there is no 7, so the probability would be 0. Probability of E equals 1. E is guaranteed. If you roll 1 dice, what's the probability that the number you get is less than 10? Well, it's guaranteed to be less than 10 because all the numbers are 6 or less. Alright, so keep that in mind. Whenever you're doing a problem and you go through this work and you get an answer for your probability, you should do a quick check in your head to make sure, is it between 0 and 1? That's a good way to know if you have the right answer or not. Alright, and this is the most important definition about probability here. It's what I call just kind of basic probability. It's called the probability of equal outcomes. And what they mean by equal outcomes, by the way, is you don't have any trick dice, right? When you roll a dice, there is a 1 out of 6 chance to get any of those numbers on the dice because you're only going to get one number, and there are 6 numbers total. And there's an equal probability of rolling any of those 6 numbers. So the basic idea of probability is this: the probability of an event is equal to the number of ways that event can occur divided by the total number of possible outcomes. So again, if we just go back to a dice, what's the probability of rolling a 3? Well, the number of ways rolling a 3 can occur is 1, because there's only one 3 on the dice, right? So when you roll a dice, one of those outcomes is what you're looking for. So the number of ways our event can occur rolling a 3 would be 1. And the total number of possible outcomes, this is the same thing as the number of things that are in the sample space. Well, when you roll a dice, there are 6 numbers in the sample space. There are 6 total possible outcomes. So you get 1 over 6, which makes sense because you have a 1 out of 6 chance of rolling anything on the dice. Alright, let's see if we can use this idea to solve a couple problems here. On page 655, number 12, it says we are flipping 4 coins. Outcomes in the sample space are represented by strings of H's and T's, such as TT, HT, HH, TT. Again, we did an example like this where we did a tree. We were rolling like a quarter, dime, nickel, or whatever. Here, they're 4 coins. They're all the same coins, and we're just interested in getting heads or tails. So TTHT would be, the first one was the tails, second one was the tails, third one was heads, and the fourth one was tails. So on part A, it's asking, how many elements are in the sample space? Well, we're flipping 4 coins, and they're just asking us for the number of outcomes, essentially. For this problem, by the way, we could definitely do a tree and figure out all the outcomes and the number of outcomes. We're going to try to get away with, for part A, for example, we're just going to do the slot method. There are 4 slots because there are 4 coins that we're flipping. Each slot has 2 outcomes, heads or tails. And the fundamental counting principle says we multiply it all together. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Alright, so there are 16 different outcomes when you when you flip 4 coins. Part B says express the event there are more heads than tails as a set. So again, if you have the tree, you can see all these events, but I think it's good to practice, in fact, trying to come up with these events without having the whole picture. So more heads than tails, since there's 4 coins that we're flipping, more heads than tails means you have to have 3 heads and 1 tail. So here's one way you could do that. The first one could be tails, and the other 3 heads. Or the second one could be tails, and the other 3 heads. The third one could be tails, or the last one could be tails. Alright, so we're doing basically a systematic listing here. I basically took the tails, put it from the first position to the second, third, and fourth. And it turns out that's all the ways you can have more heads than tails. It's all the ways you can have 3 heads and 1 tail. And I put the little curly braces at the end because that's just how we write sets. So that is now the set of all the ways you can have more heads than tails. Part C, what is the probability that there are more heads than tails? Well, we have everything we need now. We have all the ways you can get more heads than tails. Notice there are 4 ways. Hang on. Oh, there we go. I figured it out. I missed one. Obviously, you can have more heads than tails if you have all heads, right? So I forgot that you can have heads, 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 heads. There we go. So, yeah, obviously 3 heads and 1 tail is more heads than tails, but all heads and no tails is also more heads than tails. So back here in part B, we missed the all H's. So that's five ways. 5 ways we can get more heads than tails out of 16 possible outcomes. So here when they're talking about the probability that there are more heads than tails, you look for the number of ways you can do that. Well, we just figured out in part B there's 5 ways. Out of the total number of outcomes, and we figured that out in part A, there's 16. If often your probabilities will be fractions, that's fine. You must simplify them if you can. 5/16 doesn't simplify though, so that's just our answer. And then let's try part D real quick. What is the probability that there are an equal number of heads and tails? Well, if there's an equal number of heads and tails, that means there's 2 heads and 2 tails, right? Let's go through and list all the ways we can do that. So, you could have tails, tails, heads, heads. You could have heads, tails, tails, heads. And you could have heads, heads, tails, tails. Then you can kind of split them a little bit. You could do tails, heads, tails, heads. And you can alternate the other way, heads, tails, heads, tails. And then you could have, let's see, tails on the ends, tails, heads, heads, tails. We're missing a couple, let's see. And that's it, I think. That's the 6 ways you can have 2 heads and 2 tails. So if we want the probability of getting equal number of heads and tails, which is 2 heads and 2 tails, the probability will be the number of ways it can occur, which is 6, out of the total number of outcomes, which is 16. And these are both divisible by 2, so that reduces to 3 out of 8. Alright, so notice our probabilities are numbers between 0 and 1. And again, all we did is we figured out the number of ways our event can occur divided by the total number of outcomes. And we figured out that total number of outcomes in part A, right? The question was simply, how many different outcomes can you have when you flip 4 coins? Well, we started out by figuring out there were 16 outcomes, and now we're counting up all the ways our events can occur. So the events we were focused on here in part C was more heads than tails. Don't forget, it can be tricky. This was 3 heads and 1 tail, but also all heads. All of these are outcomes where there are more heads than tails, 5 different ways. And then equal number of heads and tails. That means 2 heads and 2 tails, all the different ways you can shuffle around your 2 H's and 2 T's. We came up with 6 of them, so you get 6 out of 16 or 3/8. Alright, a lot of probability problems revolve around decks of cards. So I want to remind you that a standard deck of cards has 52 cards in it. There are 4 suits. These are the hearts, diamonds, clubs, and spades. And in the suits there are 13 cards each. So those 13 cards, you have the numbers that are 1 to 10. Sorry, there is no one, I always forget, there's no one number, that's the ace technically. I think of it as the number 1. The point is the ace isn't a face card because you also have face cards which are jacks, queens, and kings. So that's important because some problems will ask you, what's the probability of rolling a face card? I just want to make it clear that those are the face cards, jacks, queens, and kings. The other thing we need to talk about are odds. Sometimes you'll be asked to find the odds against an event or the odds for an event. So if we say we want the odds against some event E, we say the odds are A to B, or A colon B. This is the way the odds are written. Now, the A here is the number of ways E cannot occur, and B is the number of ways E can occur. Similarly, if you want that's the odds against. So the odds against, the way you know the difference here, is the odds against always have the first number being the ways it won't occur, versus the odds for, the first number will be the ways it can occur. Notice, same numbers, A and B, it's just the order, right? So it can be a little bit tricky. You can basically have the same, or the right answer, just the numbers flipped. So for means the first number is going to be the number of ways it can happen. Against means the first number is going to be the number of ways it cannot happen. Alright, so let's try this out on page 656, number 17. Notice in the italics it says find the probability. We have 2 parts. Find the probability of the given event, but then find the odds against the given event. So let's start with part A, find the probability. Our event in number 17, it says we draw a heart when we select 1 card randomly from a standard 52 card deck. Okay, so our probability, what's the probability of drawing a heart? Well, it's the number of ways that event can occur. Let me go ahead and draw this out. Probability of... Oops. A little sloppy. You can name events, or sometimes I just write them in. So this is probability of drawing a heart. It equals the number of ways you can do that. Well, there are 13 hearts, so there's 13 ways we can draw a heart, divided by the total number of outcomes. And since there's 52 cards, there's 52 different outcomes. So that's it. That's the probability of drawing a heart. Obviously, you should simplify it. It actually simplifies to 1/4. That's part A. Now for part B, we want the odds against the events. So the first number is going to be the number of ways we could not get a heart. And you can do this 2 ways. Let's start with just kind of the raw numbers. If there are 13 hearts, that means there's 39 non-hearts. And I could figure that out by taking 52 and subtracting 13, right? 13 are hearts, all the other cards aren't hearts. So there's 39 non-hearts, and that's the number of ways our event cannot occur, versus the number of ways our event can occur. It's just 13, right? Because we're looking for the number of hearts. Now the thing is, just like fractions, you want to reduce your odds if you can. You can actually divide 39 and 13 both by 3, and you'll get 3 to 1. Right, so just picture that like a fraction and reduce it, and you get 3 to 1. Now, I think it makes more sense to talk about this with the raw numbers, but if you already have the probability of your event and then you want the odds, notice over here we got a simplified probability of 1/4. That means it can occur one way to the 3 ways it can, right? Because 1 and 3 make 4. So 1/4 means 1 out of 4 it'll be right, 3 out of 4 it'll be wrong, or 1 out of 4 it'll be hearts, 3 out of 4 it won't. That's also what this says, right? 3 out of 4 ways it won't be a heart, so this is the odds against, to the 1 way that it will. So it's kind of up to you however you want to think about this. I usually like to think about it in terms of the raw numbers first, right? Because literally the odds are the number of ways your event cannot happen, well, that would be 39 in this case, to the number of ways it can, which is 13, and then reduce it. But if you already have a reduced probability and you kind of know what you're doing, this is also saying one way to get a heart out of the 3 ways to not get a heart. And that's what you get here as well. So either way, our final answer here would be 3 to 1. 3 to 1 odds that we don't get a heart. Alright, page 656, number 19. This one says, assume that we're drawing a 5-card hand from a standard 52-card deck. What is the probability that all cards are diamonds? This question is a little bit more complicated because we're trying to ask a question about getting 5 diamonds in a row, or a full 5-card hand of diamonds. Let me kind of write this out for you. So what we're looking for is the number of ways to choose 5 diamonds divided by the number of ways to choose 5 cards. Now the bottom is any 5 cards, right? So there's 52 cards. Imagine all the different ways you can choose 5 cards or 5 different cards out of 52. That's a pretty complicated thing to count. So we're going to have to think back to chapter 12 and figure out if we can use a combination or permutation for this. And if we're going to do a combination or permutation, we need to know if order matters. So let's think about when you draw 5 cards in your hand, does order matter? I told you to think about, when you're trying to figure out if order matters, picture, like in this case, a hand of 5 cards, and then picture yourself rearranging your cards in your hand. And then ask yourself, now that I've rearranged them, do I still have the same hand or do I have a different hand? Well, it's pretty clear, especially for me, the first thing I do when I play cards is I usually take the cards and rearrange them in my hand. It doesn't matter how much rearranging I do, it's still the same hand. So order doesn't matter, and that's a very important thing to note here. Right? Because if I get a hand and I rearrange it, it's still the same hand, order does not matter. And if order doesn't matter, that means we can do a combination, or that a combination would be relevant in this case. So for the top, what are we trying to find a combination of? Well, we're trying to find the number of ways to get 5 diamonds out of 13 diamonds, right? So this is a combination out of the 13 diamonds that there are. We're trying to figure out how many ways can you choose 5. That's exactly what C13.5 means. Now on the bottom, similarly, we're just trying to figure out how many ways can we get 5 cards out of all the cards, which is 52. So we're going to have a combination of 52 and 5. How many ways can you get any 5 cards out of the 52? And if you throw these in a calculator, we talked about this in 12.3. You go to math, probability, and choose your NCR. So on the top you should get 1,287. On the bottom you should get some huge number, 2,598,960. And it turns out this reduces to 33 out of 66,640. I want to warn you ahead of time, there's a weird issue with the calculator where sometimes it may not take this fraction and reduce it to another fraction. It might just give you a decimal, but then your calculator is asking for a fraction reduced, which is kind of a pain. So basically, if you get a big number like this, use technology to simplify it. You can probably just throw it into Google and say simplify or something like that. But let me know if you have any issues with that or if you get any problems wrong with that. For like the exam or something, I'd be happy with this answer. I don't really care because the calculator literally won't simplify it sometimes, which is frustrating. But either way, so this is a more advanced probability problem because you have to work combinations in there. And the reason we have to is because our events are pretty complicated. Getting 5 diamonds There are 1,287 different ways you can do that. Think about what that means. That means you can get the 1, 2, 3, 4, and 5 of diamonds, obviously, but you could also get the 1, 2, 3, 4, and again, by 1 I mean the ace. So the 1, 2, 3, 4, and the king of diamonds, or the 1, 2, 3, 4, and the queen of diamonds, and all the different combinations, the 1, 5, 7, 9, right? There are a ton of different, not a ton, literally 1,287 different ways, but you have to have a combination in this case to come up with that. And again, the way we did that is, because there are 13 diamonds, we're trying to figure out how many ways can you choose 5 out of 13. Order doesn't matter, that's why it's combination. And again, on the bottom, we're choosing 5 cards out of 52, combination, because the order doesn't matter. Okay, page 658, similar problem to the last one. It says in italics, in horse racing, a trifecta is a race in which you must pick the first, second, and third place winners in their proper order to win a payoff. Right, so you're not only picking the 3 horses that are going to be in the top 3, right? You're actually picking the specific roles. You're saying that one's going to be first, that one's second, that one third. So it's probably a pretty difficult bet, I imagine. Keep in mind also, they're in proper order, right? So we already know that order matters in this case, so we're probably going to end up using a permutation. So it says if 8 horses are racing and you randomly select 3 as your bet in the trifecta, what is the probability that you will win? Assume all horses have the same chance to win. Notice that is an assumption that probably isn't true in this case, but in terms of the betting man, you probably don't know anything about the horses or whatever, and you're just kind of guessing. That's what we're assuming here. So let's think about our events here. The probability of winning in this case. So it's the number of ways you can win. Divided by number of ways first, second, and third can occur. Oops. Now, these are kind of tricky events here. The top one's tricky because it's so easy. The number of ways you can win is 1, unfortunately. Because think about it, you're picking one trifecta. You're picking 3 horses, and you're picking the order that they come in, and that either happens or it doesn't. So you're not making multiple bets here, right? It just says you pick 3 and you bet. So there's one way you can win. Now, divided by the number of ways first, second, and third can occur, well, there are a lot of different ways that can happen, right? Because there's 8 horses. How many different combinations of that can you get, where you get 3 of those 8 horses and you rearrange them in first, second, and third? Well, like we said, the order does matter in this case. I'm going to note that actually. And so that means we're going to do a permutation. There are 8 horses total, and we're trying to figure out how many different ways can we arrange them in 3 slots. So choosing 3 and shuffling them around to first, second, and third. So that's a permutation. And when we throw this in the calculator, P of 8, 3 is going to give us 336. Right. So you have a 1 out of 336 chance of winning in the trifecta. Hopefully this chapter shows you how bad gambling is. Alright, I'm not really going to do an example here, but I just want to talk briefly about Punnett squares. On page 651, there's an example that talks about them, and I basically just want to bring this up because this is a concept from biology, and it's not something we really cover in this class, and I want to make sure you're not completely confused by it. So basically, Punnett squares are what you can use when you're looking at different genes and recessive traits. So this example that they're talking about, Gregory Mendel, I think, biologist, and he was looking at seeds, and he was looking at a certain type of seed and trying to figure out if the seeds are going to be yellow or green. And it turned out that green seeds were recessive, and he showed them with a lowercase g represents the green gene, and an uppercase y represents the yellow gene. So recessive just means all of these with a y in them are definitely going to be yellow. The only time you get it green is if you have 2 green genes, right? So what that means is that the YG or the GY ones, they are carrying the green gene, but it's not showing because Y is the dominant trait. So what he has set up over here is a Punnett square, and he's got a first generation plant that happens to be a carrier, and another first generation plant that happens to be a carrier. So a YG and a YG. And then you draw this little square and you figure out all the different outcomes of their offspring. So they could have a YY offspring, which is definitely yellow. They could have a YG offspring or a GY, which is definitely yellow too because Y is dominant. Over here they could have a GY, see the intersection here, Y and G. That's another yellow because yellow was dominant. And then down here they could have a GG. This one would actually be the only green one. Notice this becomes a probability argument, right? Because we just figured out of 4, one of them could be green. So you have a 1 out of 4 chance of having a green seed. Okay? And that's it. That's just how Punnett squares work. There will be a question on my math labs, I think, that it involves Punnett squares, and they're asking you about its probability. And I just want to make sure that this whole thing doesn't look too foreign to you. So that's it. Let me know if you have any questions. Hope this helps, and keep up the good work.